In this lecture, we will discuss about three basic digital modulation schemes, which are amplitude shift keying, frequency shift keying, and phase shift keying. So the modulations can be generally divided into three: analog modulations, digital modulations, and hybrid modulations or pulse modulations. So in the classification of digital modulation, there are three basic types, which are the ASK, FSK, and PSK. So we know that modulation is the process of altering some parameter of a carrier signal according to a message signal. In analog modulation, the message signal will be analog. In digital modulation, the message signal will be digital. In both analog and digital modulations, the carrier signal will be analog in nature. You can see that the carrier signal is analog in both analog modulation and in digital modulation. In analog modulation, the message signal or the input signal is analog. In digital modulation, the input signal or the message signal is a digital signal. So this is how we express a carrier signal mathematically. You can see that it has three basic parameters, which is the amplitude of the signal, frequency of the signal, and phase of the signal. Amplitude of the carrier signal, frequency of the carrier signal, and phase of the carrier signal. We can change any of these parameters according to the message signal. So according to which parameter we change, we can classify the modulation schemes into three. If we change the amplitude, we will call it as a amplitude modulation if it is an analog modulation. If we change the amplitude according to the message signal with a digital input signal, we will call it as amplitude shift keying. If we change the frequency, we will call it frequency shift keying. If we change the phase, we will call it phase shift keying. So these are the three basic digital modulation schemes. So we will see about each of them in detail. First one is amplitude shift keying. It is the simplest digital modulation technique. The binary information or the binary signal is directly fed into the modulator to modulate the carrier signal. The carrier signal is an analog carrier signal. It is very much similar to the amplitude modulation, except for the fact that in the digital signal there are only two amplitude levels. The process can be mathematically expressed by this equation V ASK of t, meaning it is a time varying signal. V ASK of t is equal to 1 plus Vm of t into AC by 2 cos omega ct. Here this Vm of t is the input message binary signal, and AC is the amplitude of the carrier signal. Omega c is the angular frequency of the carrier signal, and time is at the time at which the signal is observed. Amplitude of the modulated signal is the output, which is mentioned as VASK of t. Vm of t is the amplitude of the input binary signal. AC by 2 is the half of the amplitude of the unmodulated high frequency carrier, and omega c is the angular frequency or 2 pi fc of the carrier signal. So the input signal or the input binary signal can take two values or two states. So if it is a bipolar signal, the logic 1 or the on state will be represented by a plus 1 volt or plus 5 volt, and the logic 0 or off state will be represented by a negative voltage. If it is a 5 volt, this will be a minus 5 volt. Since this is plus 1 volt, we have represented this as minus 1 volt. The signal can be bipolar or unipolar. If it is a unipolar signal, the positive will be represented by a plus 1 voltage, and the logic 0 will be represented by 0 volt. So in the equation we can substitute for this message signal Vm. So we have intelligently taken the amplitude of the carrier as AC by 2, because this we know that the incoming signal at the positive time or at the on state time we have amplitude plus 1 volt. So if the input signal is plus 1 volt, then this 1 plus 1 will become 2 and it will cancel this 2. So you will have a AC cos omega t carrier at the output. When the logic is 0, this input voltage will be minus 1. So this whole carrier will vanish. So here you can see the input waveform and the output modulated signal. When there is a input signal, there will be output carrier. Its value will be AC cos omega ct, and when there is no input or when there is an off state, the output will be 0. So in conclusion, the input signal can take two values, either plus 1 volt or minus 1 volt. It is also this process is also known as on-off keying, because the output modulated carrier is having either an on state or an off state. It depends on the input signal. So for the generation of ASK, we can use a simple switch as a modulator, which is controlled by a message signal. So if we have a continuous sinusoidal oscillator that produces a high frequency carrier, and we can connect a switching device in its path, and that switching device can be controlled by a unipolar or bipolar or whatever kind of message signal that we have, and we can switch on and off this device. So when the input signal is a high, you will have a output. When the input signal is low, you will not have any output. So in effect, a ASK signal can be generated. This is the simplest method of generating an ASK. ASK can take more than two values of amplitude, that is either 0 or 1 that we already discussed. If you have to represent more bits at a time, or if you want to represent 2 bits at a time, these 2 bits can be considered as a symbol. Here you have 4 symbols. So if you have 4 amplitude levels, you can represent 4 levels. So similarly, you can have any number of levels, and that much number of bits can be transmitted at a time. That means each symbol will have more number of bits in it. Now coming to the second type, which is the frequency shift keying. In frequency shift keying, as we already discussed, instead of amplitude in the ASK, we will change frequency in FSK. So this also is a simple modulation scheme. The binary signal will modulate the carrier frequency. It can be mathematically expressed as VFSK. Here it is frequency shift keying. So VFSK of t is equal to Vc cos 2 pi Fc plus Vm of t delta f t. Here you can see that the input message signal parameter is added in the frequency component, because we are changing the value of frequency here. We are changing the value parameter of frequency parameter of the carrier. That is why we added the input message signal parameter in the frequency component. In the ASK, we added the Vm of t in the amplitude parameter, because it was an amplitude modulation. Here Fc is the analog carrier frequency, Vc is the peak analog carrier amplitude of the signal, then Vm of t is the input binary signal, and delta f is the peak change in the analog carrier frequency. The analog carrier will have a constant frequency and that constant frequency will be modified to a new value according to the input signal, and the change in the value or change to the delta f, that is the change that comes in the frequency, is the delta f. So when there is an input, the frequency will vary by a value of delta f. Here we can see the governing equations. Here also we have considered the same input, plus 1 volt and minus 1 volt for logic 1 and logic 0. This is actually 0. Here when logic 1 is applied, the frequency shift will be Fc plus delta f. The new frequency will be Fc plus delta f, and when the input signal is minus 1 for logic 0, the frequency shift will be Fc minus delta f. So there will be a constant frequency Fc generated by a local oscillator. When the input is plus 1, the frequency will increase to Fc plus delta f. When the logic 0 is coming, the frequency will reduce to Fc minus delta f. So there are two frequencies in the output. In the modulated wave, there will be two frequency components. One is Fc plus delta f and Fc minus delta f. So this is the signal representation. You can see the input data 0, 0, 1, 0. So here when 0 is coming, there is a low frequency. This frequency is Fc minus delta f. When the value is 1, the frequency is a high frequency. It is Fc plus delta f. So in frequency shift keying, as we already discussed, there will be two frequencies in the output, in which the high frequency we call the high frequency as mark frequency, and the low frequency we call it as space frequency. Just two names that we call the high frequency and low frequency. Here this is the carrier frequency, original carrier frequency. This is the shift in frequency or delta f. When logic 1 is applied, the carrier frequency will increase to f1 or mark frequency, and when logic 0 is coming, it will decrease to fs or space frequency. It is space frequency, Fc minus delta f. So the overall spectrum will look like this. To generate a frequency shift keyed waveform, we can again use a switching mechanism which switches between two ports. That is, we can have two local oscillators, one generating a high frequency signal and one generating a low frequency signal. These two frequencies can be denoted by f1 and f2. f1 will be greater than f2. So if this switch can be controlled by a binary signal at signal level 1, the switch will be connected to oscillator 1, so it will give an output of high frequency, and when the binary signal becomes 0, this switch will switch to oscillator 2, which will give a output of low frequency. So according to the input signal, the modulated wave will have frequencies of high frequency and low frequency. Now coming to the third type of basic digital modulation, which is phase shift keying. In the first one we changed the amplitude of the carrier signal. In the second one we altered the frequency of the carrier signal. So obviously in this one we will change the phase of the carrier signal. So phase shift keying has many levels, which are usually called as MRI digital modulation schemes. The basic one is the BPSK or binary phase shift key, in which we use two phases. Phase change is between two levels. There can be more levels of phase changes, which are called as MRI schemes. There can be 4 levels of phase change, 8 levels of phase change, like that. advanced schemes are there. We will discuss about the basic binary phase shift keying, or it is generally called as PSK, 2 levels. So in this one phase will represent logic 1 and another phase will represent logic 0. Here, as we know, a signal have a total phase of 360 degree. Since we have only 2 levels to represent, we can place those 2 levels at maximum distance apart, which is 180 degrees apart. So we can choose like this: either at signal level 1 we will choose the output signal to be at 0 phase, and for signal level 0 the output will be at a 180 degree phase, or vice versa. So here you can see that this is the input signal. Here logic 1 high, then logic 0, logic 1, and this is the carrier signal. It is a constant frequency signal. When logic 1 is coming, there is no change in phase, and when logic 0 is coming, the phase is changed to 180 degree. There is a 180 degree shift in the phase of the carrier signal. So in the detector, if the detector will be looking for phase changes, so it can easily understand that when there is a phase shift of 180 degree, the detector can understand that it is a logic 0. So this output modulated signal will be shifting between 0 degree phase and 180 degree phase shifts. To generate a phase shift keying signal, the setup that is conventionally used is a balanced modulator. There will be a carrier wave, a single carrier wave, and this balanced modulator is capable of generating 180 degree, or for advanced modulations maybe 90 degree or 45 degree, like that it will come. For a basic BPSK modulator, the balanced modulator will generate 2 phases, that is a 0 degree, that means no phase change, and a 180 degree phase change according to the input binary sequence, so that the output wave will be having 180 degree phase shift. Now coming to the categories of phase shift keying, as I said, BPSK or simple PSK is the basic form of PSK. It has 2 phase levels. Then there can be more than 2 phase levels, that is QPSK or quaternary phase shift keying, or quadrature phase shift keying we will call it. It will have 4 phase levels. Then 8 PSK is there. So all these are generally coming under the M-array coding schemes or M-array modulation schemes. For example, BPSK, as we already saw, it has only 2 phase levels, either 0 degree or 180 degree. If it is a 4 PSK signal, here both the schemes are shown. This is a BPSK signal. In BPSK, only 2 phase levels. Here, these black ones are all at 0 degree phase, and these red ones are all at a different or 180 degree phase. Or this black one is at 180 degree phase, and this red one is at 0 degree phase. So in the right side figure, this is showing a 4 PSK signal. In this one, the signal is having 4 different phases, and it is representing 4 symbols. The first one is 0 0, second one is 0 1, third one is 1 0, and fourth one is 1 1. So the 0 0 symbol will have a phase, then 0 1 symbol will have a different phase, 1 0 symbol will have a third phase, and 1 1 symbol will have a fourth phase. That means the total 360 degree will be divided into 4. So the first symbol will be having a phase of 0 degree, second one will have 90 degree, third one will have 180 degree, and fourth one will have a 270 degree phase shift. So comparing this phase shift, the receiver can understand which symbol is coming. For example, if the receiver identifies that the incoming signal is having a phase shift of 270 degree, it can understand that a symbol 10 is coming. So this is for 4 PSK. If it is 8 PSK, the symbol level will be 3. 3 bits will be combined together to form a symbol. So at that time there will be 8 phase levels. So similarly, there can be advanced modulations. So to summarize, we have discussed 3 digital modulation schemes. The input signal will be digital, analog carrier signal will be in analog nature, and in amplitude shift scheme, keying scheme, we will change the amplitude of the carrier signal according to this binary input signal. In frequency shift keying, we will change the frequency of the carrier signal according to input binary signal, and in phase shift keying, we will change the phase of the carrier signal according to the input binary signal. So these 3 are the basic digital modulation schemes.